Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So today we will first begin with with our electricity, direct current electricity. Then we will switch to, we'll wind it down, and then we will go to magnetostatics today. So with respect to direct current electricity, the last idea that we discussed is deals with this Wheatstone bridge. Now, Wheatstone bridge is used largely, in order to understand, in order to find an unknown resistance. That's one reason and one thing to do, and also to calibrate resistances. Okay. And so, like, let's say you had three resistors, right? And the fourth resistor was a variable resistor. Okay. Then you can then use the Wheatstone bridge to adjust the fourth resistor. Or you had three known resistors, and you wanted to find the fourth resistor, value of a fourth resistor, and one of the resistors was adjustable. You know it and you can calibrate it. Then you can use it to calculate the unknown resistance. So that is the most common use of the Wheatstone bridge. But they are also used in this other two things, which one is called the meter bridge and the other is called the potentiometer. So we will go into the details of all these things as well. So we looked at Kirchhoff's laws, and then we looked at the Wheatstone bridge. Okay. So now, when we look at the Wheatstone bridge, it is typically you're looking to measure resistance in a range, with a certain accuracy. Okay. And so how do you do that? So the key thing is is first to understand what the Wheatstone bridge is. Okay. In a Wheatstone bridge, when the you connect a circuit of R1, R2, R3, and R4. Okay. And then you connect a galvanometer or an ammeter in between. Okay. And your aim is to operate the circuit in such a way that this ammeter or galvanometer has no current through it. Okay. Now, when this ammeter or galvanometer has no current, it means that R1, R2, R3, and R4 are such that, you know, the ratio of their currents are in proportion. Okay. So if I1, R1 equals I3, R3. Okay. So see what happens is you have a current coming in which breaks up into I1 and I2. Okay. Now, if I1, right, and then what then happens is there is no current in the ammeter, right? So I1 goes this way as well, right? So now what is the total, so this particular ammeter has no is like an open. There is no current through it. Okay. Now, why is that? Why is there no current through it? Right. So I1 R1 equals I2 R2. Okay. If I1 R1 equals I2 R2, right, then what can you say? Right. And I1 R3 equals I2 RX. Right. So in that circumstance, right, basically what then happens is that the voltage between these 2 points is constant. See, if I1 R1 equals I2 R2, then the drop in the voltage from this point to this point is equal to the drop in the voltage from this point to this point. Therefore, these 2 points have the same voltage. Therefore, there is no current. So when will there not be a current? When there is no difference in voltage, right? So the drop in the voltage from this common point down here, I1 R1 equals the drop in the voltage from this point to this point. So then these 2 points have the same voltage, and as a result, you don't have any current through that. Through the ammeter, right? This is if it has the same voltage, right? If 2 points have the same voltage, there's no current in between. So so this has a fixed resistance, right? An ammeter has a small but fixed resistance, right? So and of course we saw the problems dealing with the ammeter as well, right? But this is the key determinant here. So when does this happen, that I1 R1 equals I2 R2, right? So this is happens when this branch, right, this branch is acts in such a way that I1 R3 equals I2 RX. Okay, so I1 R3 equals I2 RX, and therefore R1 by R3 equals R2 by RX, and you know R3. Okay, see, Rx is unknown. You added it to the circuit, then you adjust the R3 in such a way that there is no current. And when there is no current, we all know that when this law operates and you divide the two equations, the I2 cancel, the I1 cancel, and R1 by R3 equals R2 by Rx. Okay? Therefore, when that ratio is satisfied, R1 by R3 equals R2 by Rx, or R1 by R2 equals R3 by Rx, right? You just cross multiply. R1 by R2 will become R3 by Rx, right? So then using that, you can determine what Rx is. And when you know Rx, you then, that is the aim of the whole Wheatstone bridge. It is to measure Rx, the unknown resistance. And for that, you need a variable resistance that allows you to reach that point when the ammeter goes to has no deflection. Okay, so that is the key thing. And so this is another situation, right? So this point and this point are the same as this point and this point. Okay, now R prime, right, in this case, because R, the current through this one, this automatically satisfies R1 by R by R is one, R by R is one. Therefore, there will be no current through R prime. Okay, so this is another situation, classic situation with a which is actually a Wheatstone bridge problem. They will set it up, they'll make it look like it's not a Wheatstone bridge problem, but actually it may require you to understand that when there is no current, there is a common voltage. Voltage is the same, and therefore it becomes a Wheatstone bridge problem. So that's a very, very critical situation. So in this case, you drop the R and you can pull out the R. There's no current through, and therefore the net resistance R equivalent is 2R and 2R in parallel. 2R and 2R is parallel is what? Is 2R by 2, right? R. Okay, so equal. So now there is this meter bridge. It is a modified version of the Wheatstone bridge. In this case, you're trying to measure the let's say you wanted to measure S. You knew R and you wanted to measure S. It is just a modified version of the of the Wheatstone bridge. You know, the meter bridge, this is a 1 meter length, and in that meter length, you can slide the point of contact. Okay. Now, when you slide the point of contact till the point where the ammeter reads no current, when the ammeter has no current, then R by L equals S by 100 minus L. The rows cancel. You assume that it has been calibrated so that the full length is uniform. Okay, so R by L equals S by 100 minus L, right? Or R by S equals L by 100 minus L. So if you knew S, then you can calculate R, or if you knew R, then you can calculate S, right? Because you know L, right? And then based on the value you get for L, you can then calculate the corresponding resistance. So now I'm going to introduce the next device, which is called a potentiometer. Potentiometer is not used to measure resistance. It is used to measure the EMF of a cell. Okay, the EMF of a cell is directly proportional to the length of the wire. Okay, so here also there is a Wheatstone bridge. Okay, so now here you have a resistance, resistance less by wire or low resistance wire. Then you have the voltage, which is then connected to this point. Okay, now so the APER has no current. Okay, so let's look at that. Okay, so now A uh, APER when this is connected, right? So APERG N1. Okay, so that has no current. So when does that have no current? That has no current when the ratio of the resistances is equal. So E1 by E2 equals L1 by L2. So E1 by E2 is the ratio of the two. One is you're matching the EMFs, okay, the EMF of this to the EMF of this, right? So corresponding to this, there is when you have there is a potential drop in the wire AB, right? The potential drop across AN1 is the PD, and then the potential drop across AN2, right? So corresponding to that, you end up with the with there being no the net drop across this tends to be zero. Okay, so there is a potential drop in the wire AB, right? But then when there is no current through this whole length, then you just have a single circuit. Okay, that single circuit produces the net the and this is what you call a potentiometer. It is a device whose resistance you can vary in such a way so that there is no current. So by varying this resistance, you are changing the, so there is this length plus this length, which leads to the net resistance, which will, when that is such that this whole branch does not have any current. Okay, so when that situation is reached, you then end up with your basic case, same basic case as your Wheatstone bridge. Okay? So now, when we look at you're trying to find the internal resistance of a battery. So that is another application, either the EMF of a cell or the internal resistance of the battery. So the current through AB, right? This current, right? The current through AB, right? There is null deflection is obtained, through N1. Okay, so the current through AB equals V, which is the voltage, divided by RV, the variable resistor, plus R prime. R prime is the resistance of the length of AB. So this part plus this part divided by V divided by this whole thing equals 0. And when that happens, it means that the other two parts are balanced. Okay, this part and this part and this length is balanced, and as a result, you can then say that the potential gradient is for null deflection, the gradient given by this, right, is equal to phi is equal to E equals phi times L1. Okay, when the potential gradient between these 2 points E is equal to 5 times L1, then there is no current through the galvanometer. That happens when it completely cancels out. That is, the gradient is completely canceling out the so between this point and this middle point, the gradient is such that there is no gradient between this point and this point. There's no potential in this point and this point, and this one, E, completely cancels out the voltage drop. Okay, so the voltage drop is cancelled out between A and N1, is completely cancelled out by E. So there is no current flowing through, and as a result, because there is no current flowing through, you have, uh, uh, you know, uh, you can say that through that second path, A to N1, there is no, the drop in the potential is dictated largely by this. Okay, so V I equals V divided by R1 plus RV plus R prime. Therefore, you end up with this this whole equation. Okay, so with when you have that phi, and then you have a reduced phi, that proportionately reduced phi exactly matches the voltage of E. Okay, and so that's the idea there with respect to how to find the internal resistance. Okay. The length where the deflection is obtained, where the null deflection is obtained, is measured, and then you have the corresponding resistance ratio. Therefore, the internal resistance is L1 minus L2 by L2 times R. Okay, L1 minus L2. The internal resistance here, right? This internal resistance, when you close this internal resistance R of the battery exactly matches this ratio L1 minus L2 by L2 times R. Okay. So then you have this zero, you know, and therefore E minus I prime R equals phi L2, where phi is the potential gradient across the full one length, L length of AB, the full L length of AB, right? So that is the gradient. The resistance of length AB of length L is R prime, right? Therefore, R prime divided by V plus R prime, so that you end up with the gradient. When we say potential gradient, it is the voltage per unit length. Okay, so the voltage per unit length is given by this formula, right? This is the current times R prime by L will give you the voltage. Okay, so that is the gradient. Now, once you have measured the gradient, the E is equivalent to the gradient of a portion of the length, right? E exactly matches the gradient of a portion of length. And when you need to measure the internal resistance, you close the second switch K2. First, you run it without K2, right? You leave this one open, right? You leave this one open so this R doesn't come into play. If you leave the switch open, the R will not come into play. The second case, you close the R and then you still manage to keep the current zero. It means that you have the the cell sends a current, but then there is it is correspondingly, there is still a null deflection, and that null deflection gives you a chance to evaluate R. Okay, so E equals phi L1, and therefore the corresponding R. Okay, so those are the two cases. In the first case, you're measuring the EMF, and in the second case, you close the thing and then look at the deflection, and using the deflection, you then calculate the first with you have the null deflection with the key open, and when you close the key, you then use that to calculate the internal resistance of the cell. Very interesting use of the Wheatstone bridge, the potentiometer. It is extensively used, and it is a very accurate measure. Potentiometers calibrate internal resistances very well, and it is very important application in electronics as well. Okay. So with that, I will move on to the next set of things that we want to discuss. The next set of things that we want to discuss is magnetostatics. So let me start with looking at magnetostatics. Okay, so um, when so what happened was initially they did a lot of work in electric fields, then they introduced a second situation where there is also a magnetic field. Okay, so there was this guy called Oersted noticed that a current in a straight wire causes a deflection in a magnetic compass. Okay, I times L cross B, right? And so why is there this deflection in the magnetic compass, right? So he concluded that a moving charge, the current is a moving charge, produces a magnetic field in the surrounding space. Okay, so dB, you will see Biot-Savart's law, right? Ideal cross R by R square. So that is what led to Biot-Savart's law, right? So, but this Oersted, his experiment, he found that a moving charge produces a magnetic field. The magnetic field then, in turn, exerts a force on moving charged particles. Okay, so you have a current, it exerts a magnetic field, right? Now, if you had a charged particle in that magnetic field, that charged particle will get deflected. So now, most often, you therefore end up with two fields. One is there is the electric field created by a charged particle, by moving charges, right, or any charged particle, and then there is a magnetic field as well. So now, when you have both E and B, then you can combine the two and you can write a equation, right? So you have a moving charge. Moving charge produces a magnetic field. Now, if you had a moving charge in a magnetic field, the moving charge experiences a force, okay, and that force is Q times V cross B. So now the combining of the two, we already know that in a electric field you have a charge will experience a force, right? F Q1 Q2, Coulomb's law, right? Coulomb's law is F equals EQ, can be written as F equals EQ. But then there is a second field, a second force also, that if there is a magnetic field, then it will experience a second force. So you end up with two forces. You have both a electric force and a magnetic force. Okay. Now the electric force is in a certain direction, and the magnetic force will be in a different direction. Okay. Therefore, you have all these cases. For instance, things going in a spiral loop like that. You know, those all happen because the magnetic field is V cross B. Okay, if something is moving this direction, the magnetic field will be the cross product of V and B, Q times V cross B. Combination of the two is called the Lorentz force. So what is the Lorentz force? It is the result of there being both a magnetic field and an electric field, which happens very often, right? And here is the thing. Now, a charged particle in a magnetic field experiences a force, right? Therefore, as a result, you have the Q times V cross B. Okay. So, what is the force experience? Q times V cross B. So now here there is a magnetic field B, right? And there is a um, particle which is of negative charge, right? And therefore, it is experiencing a force in the V times B, right? And because it is negatively charged, it experiences a force in this direction. If it was positively charged, it will experience force in that direction. So V cross B, if it was positively charged, it will experience force in that direction. If because it's negatively charged, it will be in the opposite direction. Okay, so now notice this field and notice the q times v cross b, and then you determine the corresponding values. So f is equal to q times v cross b, and we will from that we will determine the final results. So f, the force experienced by a charged particle in a magnetic field is given by f equals q times v cross b. We already said the force experienced by a charged particle in an electric field is F equals EQ. So therefore, you have these two results. Q times V cross B equals EQ. Now, a current carrying conductor, right? What is a current? Current is a moving charge. Moving charge in a magnetic field experience Q times V cross B. Like that, a current carrying conductor also has, what does it have? It has moving charges. In this case, Q times V cross B, there is a moving charge in a magnetic field. In this case, there is a there is a current carrying conductor, and currents are moving charges. What is a current? We looked at drift velocity and all that of the current, right? So n times q times v times d, current density, right? So the force experienced by a current is given by what, this is another form of what is called Ampere's law, I times L cross B. Okay, so if there is a current carrying conductor in a magnetic field, it too experiences a force I times L cross B, just like Q times V cross B. It is the same rule. It is I times L cross B. So the current carrying conductor will experience a force which is given by I times L cross B. Now, this is a slightly different idea. Okay? A current carrying conductor will cause a magnetic field. This is a different idea. So far we were discussing what happens to a charged particle, right? In a magnetic field. Now, here what we are discussing is, this is called Biot-Savart's law. Biot-Savart's law states that a current carrying conductor will itself produce a magnetic field. How does your fan in your room work? Current carrying conductor produces a magnetic field. Okay? And by playing two magnetic fields, they then cause a force. If there is a second conductor, right, which is in that magnetic field, it will experience a force. So that causes the fan to rotate. Or why does the fan rotate? Because there is a force experienced by a current carrying conductor. So you create the magnetic field using electromagnetics, using dB equals this, then you also put another current carrying conductor in that magnetic field, and that will experience I times L cross B. First you make the B, and then you put a conductor inside it, current carrying conductor inside the field, before you end up with I times L cross B. So, but first you must produce the field. How do you produce the field? Any current carrying conductor will itself produce a magnetic field. Okay. Now, what is the magnetic field produced by a current carrying conductor? The magnetic field is given by Biot-Savart's law. dB equals mu naught by 4 pi IDL cross R by R cubed, or IDL cross R hat by R square. Here in this case, R hat is a unit vector. In this case, we are talking about the vector R itself. So that is the R is the distance from a small piece of current carrying conductor to the particular point. So now what is the total B here? It is the sum of all the B's, dB, 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 dB. You integrate all those dBs and you will end up with and this is called Ampere's law. Okay, B dot dl is equal to mu naught I. This is all, it is related to that. Okay, so dB equals mu naught I dl cross R by R cubed. This is called Biot-Savart's law. Okay, so now if you had a circular conductor, right, the magnetic field of a circular loop, you calculate the impact of all these ideal cross R's at this point. So dl, right, is in this direction. Ideal, right, cross R is in this direction. It will go up. So it will all point to dB of Z. If you had an infinitely long conductor, you notice that at each point you have a dB in a certain direction, and several of these will cancel out in these directions, but there will be an each, you have a net component in the Z direction, and all those Z components will add up. The X direction components will all cancel because of the symmetry. Okay, so the direction components will cancel, and therefore you have a line, long, infinitely long current carrying conductor. Then the at any point like this, the B will be in that direction. Okay, so if you had a long carrying conductor, you'll have the B in this direction. This direction. This direction. Okay. So um, IDL cross R, DL cross R. Okay, so if you have long current carrying conductor, IDL cross R. Here IDL, R is there, right? The conductor is a DL cross R. Okay, so it will be in a circle around the. Okay, so that is the Z, and then and so there is another law. Okay, so in this case, he has a circular loop, right? And he has a circular loop in the XY direction. Then he's looking at all the B in the Z direction. Now, the everywhere if you had a circular loop at all these points, it will be in the Z direction. Ideal cross R is ideal cross R, ideal cross R, right? Ideal cross R, and as we said, all the XY plane components will cancel out because it's a circle. Symmetry will cause all those components cancel out, and in the Z direction, you will have a additive result. Okay. Now, therefore, if you had n wound loops, so for a single loop, you have mu naught I by 2r. Okay, and it is maximum at this point, and then it slowly goes down further. But if you had a n loops like that, then you will have a mu naught ni by 2r. If you have for n loops. For single loop, mu naught I by 2r. For n loops, it is mu naught ni by 2r. Okay, so what is the radius of the path of an electron moving at a speed in a magnetic field? Right. So this is nearly q times v cross b. Okay, calculate its energy. Okay, so in a lot of these cases, you have to understand these various rules. Okay, these various things that happen in magnetostatics. There are two things that happen in magnetostatics. First is a current carrying conductor produces a magnetic field. And second, a moving charge in a magnetic field experiences a force. And moving charge in a magnetic field is also a current carrying conductor in a magnetic field. So current carrying conductor in a magnetic field also experiences a force. So you have two different interacting things, and magnetostatics, that is moving charges, and magnetism deals with the intersection of these two different things. And you must understand both of these different things before we go into the details of Ampere's law. Okay, so at this point, see, because this is slightly complicated material, I would like to close this lecture a little early. Although this is a material that you've already learned earlier in the year, and I've taught it in great detail earlier in the year. This is something you must fully understand and absorb. Okay, magnetostatics is, you must understand the two related ideas. There are two related theorems. Okay, one is the that a current carrying conductor produces a magnetic field. dB equals mu naught by 4 pi ideal cross r by r square, where r is r hat, ideal cross r hat by r square, or ideal cross r by r cubed. It's called Biot-Savart's law. Secondly, you also have a current carrying conductor in a magnetic field experiences a force I times L cross B. A moving charge in a magnetic field experiences a force Q times B cross B. These two are related, the same idea. The other first idea that I explained, Biot's law, is that it produces a. Okay. So there is an interaction between moving charges and magnetism. Okay, that you must understand. Okay, magnetism is in some ways related to the idea of moving charges. Why are there magnets in the world which are natural? Also relate probably to charges. Magnetism has another important idea, that magnetism occurs only with a dipole. Magnetism is completely dipolar. You can never have a north pole alone. You will always have a north and a south pole. It always produces it is always diamagnetic. There is no unipoles. Okay, that is a very important law in magnetism. Okay, you will always have. If you cut a magnet, you will end up producing two north and south poles. You cut it again two north and south poles. Okay, so keep that in mind. Okay, so magnetism is the alter ego of electricity, and that's why they call it electromagnetic theory. Finally, Maxwell reduced electromagnetics to four laws, okay, which are called Maxwell's laws. So first you learn electrostatics, then you learn electrical dynamics, then you learn Ampere's law, then you learn that there's no unipoles, del dot B equals zero, then you learn Ampere's law, and then you learn there's a fourth law which is called electromagnetic induction. Electromagnetic induction is that a moving charge, right? A moving magnetic field, right? A closed loop in a moving magnetic field leads to an induced current. Okay, leads to an induced current. Okay. Now we will discuss the electromagnetic, and this is called induction, electromagnetic induction. So if there is a changing magnetic field, time varying magnetic field, in that you will experience a electric field, induced electric field. That induced electric field will lead to a current. Okay, so that is called electromagnetic induction. We will not confuse you with that. First, we will deal with a current carrying conductor produces a magnetic field. A moving charge in a magnetic field experiences a force. Okay, learn these two ideas first. This chapter 4, unit 3 is all about these two ideas. First, learn these two ideas before we go to electromagnetic induction. Okay, we will deal with electromagnetic in the next section, but first, learn these two ideas only. Okay, and then understand the two formulas involved, understand the directions involved in these two formulas. They're all cross products. Q times B cross B, ideal cross R by R cube. Two different ideas, both involve a cross product, and learn to evaluate those cross products. So my suggestion is that you take a moment to read the chapter and then look at the solved problems. Listen to the lectures. Magnetostatics is very well understood by listening to the IIT PAL lectures in our app. Okay, and once you understood that, things get pretty easy. Without understanding the three related ideas in electromagnetics, you really run into a lot of trouble. Okay, so and actually there are four related ideas. The fourth idea is of course the north and south pole idea. So understand all four ideas, and you will be in great shape to solve a lot of the problems involved in magnetostatic. But there are all these four ideas. They matter. They matter in great detail. Okay. So with that, I'm going to stop for today so that I give you a chance to become comfortable with the fact that there are four ideas, with what those four ideas are. Okay. And then today, forget about electromagnetic induction. Remember the other three ideas alone. Okay. Learn the other three ideas well. Okay. One, q times b cross b. Two, ideal cross r by r square. And three, non-existence of magnetic unipoles. Learn these three ideas and you will be in good shape to then get ready and learn the last idea, which is the interplay, the other interplay, that is a time varying magnetic field. What can a time varying magnetic field do? We'll worry about that later. Okay. Now first you learn these three ideas. They are part of magnetostatics and current, and then we will take things forward from there. With that, I'm going to stop today's lecture. But I really want you to understand these ideas and be very good with them. Okay. So I'll see you again next week.